over and over and over and over again.
One powerful example, the rhythms of the heart. Something that Boston cardiologist Ari Goldberger has been studying his entire professional life.
The neat thing about the notion of sort of the human body as a machine goes back through the tradition of Newton and the machine-like universe. So somehow we're machines, we're mechanisms. The heartbeat is this timekeeper. Galileo was reported to have used his pulse to time the swinging of a pendular motion. So that all fit in with the idea that the normal heartbeat is like a metronome.
But when Goldberger and his colleagues analyzed data from thousands of people, they found the old theory was wrong.
This is where I showed the heartbeat time series of a healthy subject. And as you can see, the heartbeat is not constant over time. It fluctuates, and it fluctuates a lot. For example, in this case, it fluctuates between 60 beats per minute and 120 beats per minute.
The patterns looked familiar to Goldberger, who happened to have read Benoit Mandelbrot's book.
When you actually plotted out the intervals between heartbeats, what you saw was very close to the rough edges of the mountain ranges that were in Mandelbrot's book. You blow them up, expand them, you actually see that there are more of these wrinkles upon wrinkles. The healthy heartbeat, it turned out, had this fractal architecture. People said, this isn't cardiology, we do cardiology if you want to get funded. But it turns out it is cardiology.
Goldberger found that the healthy heartbeat has a distinctive fractal pattern, a signature that one day may help cardiologists spot heart problems sooner.
Please look around the screen for me. All right, Cooper, we're going to do the calibration.
At the University of Oregon, Richard Taylor is using fractals to reveal the secrets of another part of the body, the eye.
What we want to do is see what is that eye doing that allows it to absorb so much visual information. And so that's what led us into the eye trajectories. Under the monitor is a little infrared camera which will actually monitor where the eye is looking, and it actually records that data. And so what we get out is a trajectory of where the eye has been looking.
Well, it's interesting how they go around the pattern.
And so the computer will get out this graph, and it will look, have all of these various little structure in it. And it's that pattern that we zoom in, we tell the computer to zoom in on and see the fractal dimension.
The tests show that the eye does not always look at things in an orderly or smooth way. If we could understand more about how the eye takes in information, we could do a better job of designing the things that we really need to see.
A traffic light. You're looking at the traffic light, you've got traffic, you've got pedestrians. Your eye is looking all over the place, trying to assess all of this information. People design aircraft cockpits, rows of dials and things like that. If your eye is darting all around based on a fractal geometry, though, maybe that's not the best way. Maybe you don't want these things in a simple row. We're trying to work out the natural way that the eye wants to absorb the information. Is it going to be similar to a lot of these other subconscious processes? Body motion. When you're balancing, what are you actually doing there? It's something subconscious and it works, and you're stringing together big sways and small sways and smaller sways. Could those all be connected together to actually be doing a fractal pattern there? More and more physiological processes have been found to be fractal.
Not everyone in science is convinced of fractal geometry's potential for delivering new knowledge. Skeptics argue that it's done little to advance mathematical theory. But in Toronto, biophysicist Peter Burns and his colleagues see fractals as a practical tool, a way to develop mathematical models that might help in diagnosing cancer earlier.
Detecting very small tumors is one of the big challenges in medical imaging.
Burns knew that one early sign of cancer is particularly difficult to see: a network of tiny blood vessels that forms with the tumor. Conventional imaging techniques like ultrasound aren't powerful enough to show them.
We need to be able to see structures which are just a few tenths of a millionth of a meter across. When it comes to a living patient, we don't have the tools to be able to see these tiny blood vessels.
But ultrasound does provide a very good picture of the overall movement of blood. Is there any way, Burns wondered, that images of blood flow could reveal the hidden structure of the blood vessels? To find out, Burns and his colleagues used fractal geometry to make a mathematical model.
If you have a mathematical way of analyzing a structure, you can make a model. What fractals do is they give you some simple rules by which you can create models. And by changing some of the parameters of the model, we can change how the structure looks.
The model showed the flow of blood in a kidney, first through normal blood vessels, and then through vessels feeding a cancerous tumor. Burns discovered that the two kinds of networks had very different fractal dimensions.
Instead of being neatly bifurcating, looking like a nice elm tree, the tumor vasculature is chaotic and tangled and disorganized, looking more like a mistletoe bush.
And the flow of blood through these tangled vessels looked very different than in a normal network. A difference doctors might one day be able to detect with ultrasound.
We've always thought that we have to make medical images sharper and sharper, ever more precise, ever more microscopic in their resolution to find out the information about the structure that's there. What's exciting about this is it's giving us microscopic information without us actually having to look through a microscope.
You can see it rises up as the bubbles.
We think that this fractal approach may be helpful in distinguishing benign from malignant lesions in a way that hasn't been possible up to now.
It may take years before fractals can help doctors predict cancer, but they are already offering clues to one of biology's more tantalizing mysteries. Why big animals use energy more efficiently than little ones? That's a question that fascinates biologists James Brown and Brian Enquist and physicist Jeffrey West.
There is an extraordinary economy of scale as you increase in size.
An elephant, for example, is 200,000 times heavier than a mouse, but uses only about 10,000 times more energy in the form of calories it consumes.
The bigger you are, you actually need less energy per gram of tissue to stay alive. That is an amazing fact. This is a very tiny number.
And even more amazing is the fact that this relationship between the mass and energy use of any living thing is governed by a strict mathematical formula.
So far as we know, that law is universal, or almost universal, across all of life. So it operates from the tiniest bacteria to whales and sequoia trees.
But even though this law had been discovered back in the 1930s, no one had been able to explain it.
We had this idea that it probably had something to do with how resources are distributed within the bodies of organisms as they varied in size.
We took this big leap and said, all of life in some way is sustained by these underlying networks that are transporting oxygen, resources, metabolites that are feeding cells. Circulatory systems and respiratory systems and renal systems and neural systems. It was